In this lecture, we'll discuss molecular geometry. So if you remember in the last lecture, we talked about hybridization. In there, I mentioned that a molecule with a certain hybridization has a specific structure, but that is not the case all the time. So to make sure that we understand this much more clearly and to apply it to all the cases, we use a theory called the valence shell electron pair repulsion theory, or VSEPR theory. So what does that state is that valence electrons, shared and lone pairs, always try to repel each other. So always remember that electron is a negatively charged molecule, so a negatively charged particle, and two electrons always try to repel each other. So to determine the molecular geometry, so we always start with understanding the steric number. So steric number is given by the number of pi bonds, the number of sigma bonds, plus the number of lone pairs. So this is the formula for the steric number. So the number of sigma bonds plus the number of lone pairs. So in general, there are three general steric numbers. For example, the common numbers are 4, 3, and 2. These are the three general forms of steric numbers. So whenever we talk about these steric numbers, always understand that steric number refers to the understanding that we are trying to find the number of sigma bonds and the number of lone pairs. For example, let's take the example of methane. Methane in general has 4 sigma bonds and 0 lone pairs. So it contains a steric number of 4. Notice that every single bond, so single bond or a double bond or a triple bond, all of them always only represent one bond. So one sigma bond. So whatever the case is, they always represent one sigma bond. Now let's take ammonia. So let's take ammonia. Ammonia has 3 sigma bonds. So 3 sigma bonds, but it has a lone pair of electrons on the top. So that becomes 1. So you get a total of 4. Next, a molecule of H2O has 2 lone pairs of electrons and it has 2 sigma bonds. So that gives a steric number of 4. All molecules with steric number 4 always have an sp3 hybridization. And all molecules with an steric number of 3 always have sp2 hybridization. In the same way, all molecules with steric number 2 always have sp hybridization. Now, understanding hybridization here, why is it important? Because every time you come across a steric number, you always know the hybridization corresponding to it, so that it's easy to find out the hybridization as well. For example, we can simply write that all these three have the same sp3 hybridization. Even though they do not have the same number of bonds, they still have the same hybridization. Now let's talk about the molecular geometry of sp3 molecules. For any sp3 molecule which has 4 valence electron pairs, will always form a tetragonal electron group geometry. For example, CH4 has a tetragonal structure. But when the same case comes to ammonia, what happens here is that notice that the bond angle is 107. Originally it was 109.5. What is happening here is that the lone pair of electrons on the top is repelling the molecule away from it's basically trying to push it downward. That's why it reduces the angle. So as the number, so lone pairs reduce the bond angle. Lone pairs always try to reduce the bond angle. Now, so we have, let's talk about a H2O molecule. H2O has 2 different electron pairs. That's the reason why it's much smaller than the ammonia molecule, because there are 2 different electron pairs that are trying to repel the sigma bond formed with the hydrogen. So that's why there's much less of an angle. So the higher the number of lone pairs, the smaller the bond angle with respect to the one which does not have any lone pairs of electrons. Now, the molecular geometry in general is described for only the atoms that are bonded to the central atom. So whenever the electron group geometry includes lone pairs, then we'll change the name of that structure. if you have 4 bonding electrons and 0 lone pairs, and the steric number will be 4, so the predicted arrangement is a tetrahedral arrangement, but the molecular geometry is tetrahedral, so it will stay the same. But you increase the number of electron pairs, what happens is that they change the atomic structure. So when you have a 3-1 structure with respect to the number of bonds, sigma bonds, and the electron pairs, so then that results in a trigonal planar structure. So trigonal pyramidal structure. When you have a 2-2, structure, so that results in a bent or V-shaped structure. In the same way, when you have a steric number of 3 and the number of electron pairs is 0, then you have a trigonal planar structure. So notice that all of these are steric number 4, but only when you have steric number 3, the general structure is trigonal planar. And when you have a steric number of 2, then the structure is linear. So this is how we generally come across the molecular geometry of different atoms. So for example, here this is an example of a trigonal planar structure. So the general angle without any lone pairs when you have a steric number of 4 is 109.5 degrees. And they have a steric number of 3 generally is 120 degrees. And when you still have a steric number of 2, it's generally 180 degrees. So this is the bond angle with reference to the steric number, provided that there are no electron pairs. So when you have increase in the electron pairs, when the electron pairs start to increase, the bond angle will start decreasing. Right? The bond angle will start decreasing. So try this problem and try to understand what would be the structure and try to predict the structure. Next, let's talk about SP geometry. SP geometry is generally a linear structure because a steric number of 2. Notice that there is no lone pairs and there are 2 sigma bonds. So it has a total of 2 different sigma bonds. That gives a SP hybridization. That gives you a total of. So understand that whenever you have a bond, we only count the sigma bonds. We do not count the pi bonds. Always remember, always count sigma bonds, right? Not pi bonds. So for example, even if you have a triple bond, so even triple bond is only counted as one bond, one sigma bond. Even if it's a double bond, it's only counted as one sigma bond. Whatever the case number of bonds is, it's always going to be one sigma bond. So this is the summary and the structures. I've given it as an example. So if you want to go through it again, just pause the video right here and just review everything that you see on the slide. So next, let's talk about polarity and dipoles. So what is molecular polarity? So molecular polarity is the basis of understanding how does the charge differentiate inside a molecule. So we discussed this when we discussed about polar covalent bonds. So when we're talking about polar covalent bonds, I told you that certain molecules, for example, carbon, oxygen, have always tried to have an electronegativity difference, so difference in electronegativity, that's greater than 0.5. When you have a greater than 0.5, but when you have an electronegativity that's less than 1.7, I told you that the bond is called as a polar covalent bond, or in simple terms, we call it a polar bond. So these polar bonds, what they'll do is they'll differentiate the charge, so creating a partial positive charge on the carbon and a partial negative charge on the oxygen. This process of shifting the electrons towards one side is called induction. So this induction results in a specific characteristic of a molecule called the dipole moment. So the dipole moment can be written as the amount of the charge, the partial charge, times the distance between the partially charged molecules. Right? So these generally are measured in a unit called dBi. dBi is 10 power negative 18 ESU per centimeter, ESU through a centimeter. Now, how do you calculate the dipole of a methyl chloride molecule? So we know the charge, we not need to know the charge and the distance. So when you calculate the value, you get 1.056 into 10 power negative 10. and 1.772 into 10 power negative 8. This results in a final value of 1.87 dBi. This 1.87 dBi is what we are trying to understand as the main value. Now, the same thing, if it were 100% ionic, the charge will be really high. So, which means that it would be 8.51. Now, what we are trying to do here is trying to understand how much, so how ionic is the molecule. So, what we did in the first part is we did not shift all the electrons towards it, we gave it an even share. But now we shifted all the electrons towards the chlorine and tried to understand what would be the dipole moment. The ratio of the polar structure divided by the ionic structure is called as the ionic character. So which means that the molecule shows a 22% ionic character. Whatever the rest is left is called as the covalent character. So whenever you have a molecule, this is how the molecule in itself shows differentiation in the structure in which they operate. Next, let's talk about the polarity of some other common bonds. For example, C bond O has a bond length of 1.41. It has an observed dipole moment of 0.7. So when you calculate the percent ionic character, you get about 10%. But the same C double bond O has a 41% character. The reason is the shortening of the bond length. So that shortening of the bond length increases the observed dipole moment by fourfold, by 4 times. The same thing with oxygen and hydrogen as well. So this also increases to 33%. So depending on the molecules that are bonded, the chances are you see that there is a much differentiation between the ionic character. The more ionic character, so the higher the ionic character, so the more prominent the polar bond. So the more prominent the polar bond. For some molecules, they can have multiple polar bonds, and the dipole moment will become the vector sum of all the individual bond dipoles. For example, this carbon and chloride and this carbon and chloride are two different molecules with two different electron densities, but when they combine, you get a resultant dipole moment. So this value is called as the resultant dipole moment. It's still there, but it combines together. But the same thing when you talk about, let's say, ammonia. Ammonia here has a dipole moment with nitrogen and also has a dipole moment with the electron pair. So the net dipole moment will always be upward. So the net dipole moment will always flow upward. Remember that when we talked about this already. This part represents the partial positive charge and the arrowhead represents the partial negative charge. In water molecule also the same thing. It also has a net upward dipole moment coming down from hydrogen. Now, what does this have to do with the molecular geometry? So, understanding the molecular geometry helps you in understanding how the net dipole moment works. So, if you know the structure that it's tetrahedral, then you know that it's going to be a little upward or downward depending on the structure. Now, once we know the general structure of the arrow, we can also plot the electrostatic potential map. Electrostatic potential map shows you the differentiation of the charge that's sitting on the molecules. For example, when you take a molecule of chloromethane, notice the red here. The bright red represents the most negative and the bright blue represents the most positive. But notice that the differentiation between the charge, a neutral molecule will look, so a neutral molecule would look green if it had no polar covalent bonds at all. Because there is a polarity, what happens now? There is a large accumulation of negative charge on the top, and there is a large accumulation of positive charge on the bottom. This is what creates the polarity. Polarity refers to the charge. Polarity refers to the charge. So the same way, when we talk about different molecules, for example, acetone has 2.69. One of the molecules that has, for example, pentane as a covalent bond has 0 dBi. Carbon tetrachloride, because carbon CCl4 becomes 0. Why is it the case that CCl4 has 0 dBi? The reason mainly is because even though carbon chlorine have a partial charge difference, so the partial charge difference What happens here is that because all of them have the same dipole moment, so because they have the same mu value, they'll cancel each other. Even though the individual bonds are polar, the net polarity of the entire molecule is zero. The net polarity of the molecule is entire zero because they cancel each other. So this is the idea behind molecular polarity. So in this lecture, let's discuss intramolecular forces. So we talked about many properties in general, such as solubility, boiling point, density, and state of matter, melting point, are all generally affected by the attraction between the molecules. So whenever you think of physical characteristics are generally affected by the intramolecular forces. Understand there are two words, intra and inter. Inter refers to between the molecules. Intra refers to the internal structure of the molecule. So internally, inside the molecule or inside. So we are talking about the forces between molecules. There are neutral molecules that are attracted to one another by dipole-dipole interactions, hydrogen bonding, and dispersion forces, or what we call London forces. What happens here is, let's talk about the first one, dipole-dipole attractions. So we talked about molecules such as acetone, which have a partial negative charge on the bottom and a partial positive charge on the bottom. What happens here is that the negative charge attracts the positive charge of the other molecule, and the positive charge gets attracted towards the negative charge of the other molecule. This creates what we call a dipole-dipole force. So the force between the negative and the positive is called as a dipole-dipole force. And the polar molecules will line up their opposite charges, and this creates acetone's permanent dipole that results from the difference between the electronegativity between carbon and oxygen. This dipole-dipole attractions between acetone molecules, what will they do is, one, it increases the acetone's boiling and melting points, and also similar molecules without dipole-dipole interactions such as isobutylene have lower boiling and melting point. For example, the structure looks both similar. The only difference is that it has CH2 and here there's an oxygen. So notice the melting point difference here and a boiling point difference here. Why is boiling point important? Because at room temperature, this is a liquid, but at room temperature, isobutylene is a gas. So this is the idea behind the physical nature of the molecule and how the intermolecular forces have a key role in that. Next, let's talk about another type of intermolecular force called hydrogen bond. Hydrogen bonds are especially strong type of dipole-dipole attractions, and these are strong because the partial positive and the negative charges are relatively large. Why is that the case? The hydrogen bonding is basically the attractive force between the hydrogen bonded to an electronegative atom and a lone pair of electrons on the electronegative atom. For example, if you take a water molecule has a partial positive side and a partial negative side. The lone pairs with a partial negative charge attract the the hydrogen connected to the oxygen, which has a higher electronegativity. Understand that the only requirement for hydrogen bond is one where the hydrogen should have been bonded to an electronegative atom, so a high electronegative atom, and it should have a lone pair in the proximity. So here we have classified both. One, hydrogen is bonded to oxygen, which has high electronegativity. And number two, there is a lone pair of electrons. So therefore, it creates a hydrogen bond. This hydrogen bond is the one that makes water different from other quantities. So when you take water or when you take ammonia, anything that contains oxygen, anything that contains a highly electronegative atom bonded to a hydrogen will create hydrogen bonds. So this is the idea behind some of the common interactions that you'll generally see. So only when a hydrogen shares electrons with a highly electronegative atom will it carry a large partial positive charge. So this large partial positive charge can attract large negative charges that creates the attractions. So even with large partial charges, hydrogen bonds still have to be about 20 times weaker than that of covalent bonds. Notice that hydrogen bonds are still intermolecular forces, not intramolecular forces. So the solvents that engage in hydrogen bonding are called as protic solvents, and solvents that do not have hydrogen bonds are called as aprotic solvents. So you will need to learn this, remember this, because we'll come back to this again in chapter 7 when we discuss nucleophilic substitution and elimination. So whenever we talk about protic is where there can be hydrogen bonds. Aprotic are ones that do not have hydrogen bonds. So for example, diethyl ether is a molecule, is a common molecule that does not have solvent, that does not have hydrogen bonds. The same with dimethyl sulfoxide or DMSO. That's also an aprotic solvent. So trimethylamine is a molecule that can have a higher boiling point. So the more the number of hydrogens, so the higher the hydrogen bonds. So the higher the boiling point. So remember that as the number of hydrogen bonds is depends on the number of hydrogens. So which means that hydrogens decide the number of hydrogen bonds, which creates different isomers with different boiling points. These are the main bonds that cause the DNA to form the double helix structure. So what happens here is the proteins that are present inside the molecule will share its AT. So for example, if you remember in your, in your DNA, you have ATGC. AT has 2 hydrogen bonds. The GC forms 3 hydrogen bonds. So this is how a double helix structure is formed. So this is where you find A and T and G and C. So this is how you get the general structure of your DNA to form an alpha helix protein structure. Next, last force is London dispersion forces. So London dispersion forces are special because these are dipole forces in a non-polar molecule. How does that happen? If you have 2 molecules that are non-polar, they still have an attractive force between them. This occurs because it can create an induced transient dipole moment, and that dipole moment is called as London forces. So non-polar molecules normally have their electrons that are spread out. So they generally have electrons so that are generally spread out evenly around the nuclei compared to the balancing the charge. But the electrons are in constant random motion within their molecular orbitals. So what that does is it creates an uneven distribution. So because of that constant random motion, it creates an uneven distribution of the molecule electrons. And once the uneven distribution happens, it creates what we call as a temporary dipole. What happens here? A lot of negative charge accumulates on one side, and a lot of positive charge accumulates on the other side. This creates a temporary dipole. Because the area is larger, it's not easy to diffuse this force. That's the reason why they try to bond to each other. That creates the London dispersion forces. The name itself says dispersion, meaning that the larger the molecule, so larger the molecule, the larger the force. So such fleeting attractions are generally weak. But because when you have a weak interaction, but if there are enough of them, so that can also add up to a significant part of the structure. So a gecko is generally, a lizard in general, they can create this by the London dispersion forces. So the greater the surface area of the molecule, the more temporary dipole attractions are possible. So the feet of the gecko always tries to have flexible hair. That flexible creates maximum surface contact. That's how it's able to support the entire weight, because there are so many of those hair, small hair, that can support the entire weight of the gecko. So London dispersion forces are also the reasons why molecules with more mass generally have higher boiling points. For example, hexane has a boiling point of 69 degrees, but pentane has only 36, but butane has about 0, which means that the number of carbons, so as you increase the number of carbons, the boiling point will increase. The reason is because the London forces are increasing as you go along the structure. The same thing happens with the surface area. Even though if you have the same number of carbons, the larger the surface area, the larger the force. For example, pentane, 2-methylbutane, and 2,2-dimethylpropane also have the same number of carbons, the same number of hydrogens, but the only thing that does not have it is that the surface area. So as the surface area reduces, automatically the London force starts to decrease. So let's finally talk about solubility. So we talked about in general chemistry, in general, that like dissolves in like, which means that if it's a polar compounds always try to dissolve in polar compounds. A non-polar compound always try to dissolve in non-polar compounds. So if you have compounds that mix well, that are all capable of hydrogen bonding and a strong dipole-dipole moment, so there is no reason why they shouldn't mix. In the same way, a non-polar molecules, if none of the compounds are capable of forming strong attractions, then no strong attractions would have to be broken to allow them to mix. So this is the idea behind solubility. So, but there are molecules that can create what we call amphiphilic nature. Amphiphilic nature is where it can be both hydrophilic and hydrophobic at the same time. So an example of that is a soap molecule. So if you take a soap molecule, the soap molecule generally has a nonpolar part, which is the fatty acid part, and it has a hydrophobic part, which is COO minus, hydrophilic part, which is the polar part. So which means that the hydrophobic part attracts the nonpolar parts. The hydrophilic part attracts the polar parts. So whenever you mix it with oils, the oil molecule gets surrounded with the fatty acid structure, creating a ring. This is the type of ring that you also see in cell membranes. The layers that you generally see there are called phospholipids, representing the two parts, the lipids, which are hydrophobic, phosphates, which are hydrophilic. So notice that this is the cell membrane. This is the molecule that separates cell membrane from the external to the internal cell, ECF to the ICF. So this is how soap molecules organize into the micelles in water, which form a non-polar interior to carry away dirt. So micelles are basically ring structures around the non-polar molecule created by an amphiphilic substance. So that ends the chapter on a review of general chemistry. So with that, I'll see you again in the next lecture.